One observation that's going to be very important and that I'm going to dwell upon in detail in the forthcoming discussion is that, and also be mindful of the fact that the principal diagonal terms, if off diagonal or anti-principal diagonal terms also get populated, what happens to the square space? And also by now you would have understood that if I were to include instead of 2 by 2 n, then the square space would have had the area Now let's look at this basic transformation. That is, we have understood very categorically in our beginners module that when a matrix operates on a vector, you get a scaled vector. Of course, a scalar multiplier lambda is used here. It multiplies the vector. Now let's try and adopt this idea in the context of transformation of two-dimensional entities. Now the first transformation that I am going to attempt is the transformation of the given square space defined by two vectors into a bigger square space. Now the transformation matrix, in order to facilitate that transformation, is given by this particular matrix. One observation that's going to be very important and that I'm going to dwell upon in detail in the forthcoming discussion is that the off diagonal or anti-principal diagonal terms are 0 and only the principal diagonal terms are populated, and also be mindful of the fact that the principal diagonal terms are equal to each other. So now let's see what exactly happens. If you look at the square space defined by two vectors, one vector with unit magnitude along x-axis, another vector with unit magnitude along y-axis, they are given by 1, 0, vector 1, and this is vector 2. This is the horizontal vector and this is the vertical vector, and they go to clearly define a square space. Now my job is to scale this vector space into a bigger square space, and the scaling I have chosen here is 2. Let's see how exactly it works. Now, going by the definition of transformation, I am trying to transform this horizontal vector with the magnitude 1 along x and 0 along y, and the transformation matrix, as I have explained, is 2, 2, 0, 0. When this transformation matrix operates on this, going by the basic multiplication, of course when I multiply row by the column, it is nothing but the dot product, and when I do that, I get 2 into 1 plus 0 into 0, I get 2, and when I do that for the second row, 1 into 0 plus 2 into 0, that turns out to be 0. That means very clearly this particular vector is being scaled by the first column. That is, this column is scaling this particular x vector. And similarly, when I operate the vector along the y-axis with 0 magnitude along x and magnitude 1 along y by this particular transforming matrix, then I would get 0 and 2, because when I multiply the column with the first row, I get 0, obviously 0 into 2 plus 0 into 1, and when I multiply the second row, 0 into 0 and 2 into 1, and again it clearly goes to say that it is the second column that is actually scaling this particular vector. So this column is scaling x and this column is scaling y. And if I define the new vector space that is defined by this scaled vector along x and scaled vector along y, you would see a bigger space. And if I put these into the matrix form, these vectors into matrix form, I would be getting back to this particular transformation matrix. And if you observe that the determinant of this particular matrix, which is nothing but 2 into 2 minus 0, which is 4, is nothing but the area of that particular square. And one observation that must very categorically be done is that the ratio of the new square space divided by the original square space area is nothing but 4:1, which we now concluded is nothing but the determinant of the scaling matrix. So this is one simple example where there is no distortion, there is only a linear scaling, that is, only the principal diagonal elements are populated. We would see in the next discussion if off-diagonal or anti-principal diagonal terms also get populated, what happens to the square space, whether it remains a square or becomes distorted, by what angle, how, all those discussions would follow. From this discussion, two reckonings are categorical. We saw that the first column in fact scaled the x vector and the second column scaled the y vector, and also we saw that there was no distortion owing to the fact that off-diagonal terms are not populated, which you would experience in the next transformation. And the most important fact that you got to take away here is the determinant of the transformation matrix is the scaling factor for the area. Because if you looked at both the square spaces, the first square space has unit area and the second square space has got a 4 unit square area. So that means the ratio of their areas is nothing but the determinant of the transformation matrix, and therefore this is also deemed upon as scaling matrix. So now let's see how to produce a rectangle. What would be the transformation? Of course, you will have to scale the vector space in two different directions differently. You cannot have uniform scaling factors. And also by now you would have understood that if I were to include instead of 2 by 2 n, then the square space would have had the area n square after transformation. That means the scaling would have been a generalized scaling. That means instead of 2 2 you could have had n, and in that case also the determinant is nothing but n square, which could have been the scaling factor. So let's continue.